Good day everyone. We are the Group 7 to report the earthquake effects and design of structures. First, what is earthquake? Earthquake is a natural phenomenon which can occur anytime and anywhere, and also known as a quake, tremor, or a temblor. From the word earthquake, ito ay yung pagyanig o isang lindol ng surface of the earth. An earthquake is what happened when the two blocks of the earth suddenly slip past one another, and the surface where slip is called the fault or the fault plane. Tapos doon nagaganap yung ground shaking na kung saan ito yung primary cause of earthquake damage to the man-made structure, and many factors influence the strength of the earthquake shaking at a site. Effect of earthquake on buildings. Alam naman natin na malaki ang epekto ng earthquake sa isang structure. At nabanggit nga kanina na earthquake is directly affect ground shaking. At mayroong iba't ibang panganib na maaaring idulot ang isang lindol. Una ay ang pagyanig or ground shaking. Pangalawa ay yung pagbitak ng lupa or the rupture, at ang paglambot ng lupa or the liquefaction, at ang pagguho ng lupa or the landslide, at ang tsunami. Why does a building collapse? The response of a structure to an earthquake is a function of the nature, tulad na lang ng foundation of soil, material, form, size, and mode of construction. Ayun yung nagiging response ng isang building sa earthquake. And also, most collapses that occur during earthquake are not caused of the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and the lower levels, and sending shock waves through the rest of the structure and causing it to vibrate back and forth. These are the different types of materials used in building construction. These type of materials are used in effect on how a building performs during an earthquake. And it has a wide range of physical properties. These materials are brick, wood, and steel, concrete, stone, and aluminum, plastic, adobe, tiles, and bamboo. For example, the brick masonry is very stiff but can fracture under the earthquake forces, whereas the wood cannot support as much the weight but is more flexible, depending on how much the steel reinforcement is used. Reinforced concrete can be made to be either very stiff or somewhat flexible. We all know that the architect and the structural engineer can design the building to resist the deformations during an earthquake. If the building is stiff and strong and only a few floors tall, the shaking you feel may not very different from somewhat standing outside. At alam naman natin na yung earthquake is a natural disaster na kung saan suddenly and dangerously powerful. When designing earthquake-resistant building, and safety professionals recommended adequate vertical and lateral stiffness and strength, especially lateral. So, sa isang structure, kailangan talaga natin na alam natin at pinag-iisipan natin kung paano mapapatibay at hindi maguguho ng mararanasan natin na earthquake.
So now we will proceed to the effects of earthquakes. We have primary and secondary effects. So for primary, we have ground shaking, ground rupture, landslides, tsunamis, and liquefaction. And for secondary, we have fires. So for ground shaking, it is the most familiar effect of earthquakes. It is a result of the passage of seismic waves through the ground and ranges from quite gentle in small earthquakes to incredibly violent in large earthquakes. Buildings can be damaged or destroyed. People and animals have trouble standing up or moving around, and objects can be tossed around due to strong ground shaking and earthquakes. And usually, saka natin nasasabi na mayroong earthquakes once na nafe-feel natin yung ground shaking. And dito nga yung mayroong mga different intensities and magnitudes. And itong makikita natin sa picture ay isang situation na nangyari dahil ng isang earthquake kung saan yung upper level of the two-level structure has collapsed onto the lower level as a result of failure of the support columns. The columns failed partially in response to ground shaking noong October 17, 1989 na earthquake, and dahil doon sa failure ng support columns ay 41 people were killed. So next, we have ground rupture. Ground rupture occurs when the earthquake movement along a fault actually breaks the Earth's surface. Although active ground rupture is comparatively rare, there have been cases of it in California. Rupture causes problems for humans by rupturing pipelines, tunnels, aqueducts, railway lines, roads, and airport runways which cross an area of active rupture can easily be destroyed or severely damaged. So unlike ground shaking, which is a very common effect of earthquakes, yung ground rupture ay mas rare. And kagaya na makikita natin dito sa picture, yung certain part ng lupa ay bumagsak, and dito na-form yung scarp or yung kung saan merong part ng lupa na matarik and merong malalim, and makikita natin na intact pa din naman yung bahay na nakatayo dun sa gitna kahit na nagkaroon ng 2 to 3 meters offset. Pero ito ay dangerous pa din para sa mga tao kasi syempre yung mga pipelines or yung lines na nasa ilalim ay once na mapinsala ay magkakaroon din ng mga problema. Next, we have landslides. Landslides are caused by earthquakes both by direct rupture and by sustained shaking of unstable slopes. They can easily destroy buildings in their path or block roads and railroad lines or take hilltop homes with them as they tumble. They even can dam rivers on occasion. So, ang landslide or pagguho ng lupa ay isa ring common effect ng earthquake na makikita din natin dito sa Pilipinas kagaya ng nitong aerial shots ng earthquake-induced landslides na nangyari sa Makilala, Cotabato. So, ang landslides ay delikado syempre para dun sa mga bahay na nakatayo sa tuktok ng mga bundok or ng hill. Kasi once na nagkaroon ng landslide, pwedeng makasama yung kanilang mga bahay, and ganun din naman yung danger na nakatayo sa ilalim ng mga bundok kasi once na gumuho yung lupa, sila yung pwedeng matabunan. And ang landslides din ay isang pwede maging problema dahil pwede ma-block yung roads na kung saan maaaring ma-stranded yung mga tao na dadaan, and pwede rin siyang maka-cause ng problem sa mga rivers. Next, we have tsunamis. So, tsunamis, which are popularly and incorrectly known as tidal waves, are a grave hazard to many parts of the world, particularly around the Pacific Ocean basin. Tsunamis are a series of water waves caused when the seafloor moves vertically in an earthquake and which can travel vast distances in a short period of time. Remember that tsunamis are a series of waves and may start with a gentle withdrawal of water followed by a very abrupt arriving wave followed by another withdrawal. So, kagaya ng pinanood sa atin ni Sir noon, kung saan bago nagkaroon ng tsunami ay napansin na yung tubig sa dagat ay umuurong na. So, once na makita natin na ganun, dapat yung mga tao na malapit sa mga dagat ay mag-evacuate na or mag-move sa higher places kung saan hindi sila maapektuhan ng mga rumaragasang tubig. Pero kagaya nga nung sobrang lakas ng mga tsunami kung saan yung mga bahay na mismo yung nadadala ng tubig. And itong picture is taken nung nagkaroon ng tsunami sa Hawaii noong 1946, which is generated by a magnitude 7.8 earthquake, and the tsunami height is about 6 meters or 20 feet. Next, we have liquefaction and subsidence. Liquefaction and subsidence of the ground are often the cause of much destruction in earthquakes, particularly in unconsolidated ground. Liquefaction is when sediment grains are literally made to float in groundwater, which causes the soil to lose all its solidity. Subsidence can then follow as the soil recompacts. All of these effects pose a grave danger to buildings, roads, train lines, airports, runways, gas lines, etc. So, ang liquefaction ay yung paglambot ng lupa dahil sa earthquake. And ito ay delikado kasi syempre once na lumambot yung lupa, maapektuhan yung mga buildings or yung lupa na pinagtayuan ng mga buildings and yung mga gas lines sa ilalim. Kagaya ng makikita natin sa picture, ito po ay isang um, apartment sa Japan kung saan hindi mismo nasira yung building pero siya ay nag-tilt ng 75 degrees from the vertical and sabi po doon ay yung mga tao ay nakalabas pa din doon sa apartment kasi hindi naman totally nag-collapse yung building kundi siya ay nag-tilt lamang dahil nga sa liquefaction and subsidence ng lupa na dulot ng earthquake. So, for the secondary effect of earthquakes, which is fires, fires are a major source of damage after earthquakes. Ground rupture and liquefaction can easily rupture natural gas mains and water mains, both contributing to the ignition of fires and hindering the efforts to control them. In an amazing example of this, during the 1994 Northridge earthquake, there were actually places where water was pouring down streets from broken water mains, and at the same spot and same time, fire was roaring out of ruptured gas mains. So, possible din na magkaroon ng fires kasi once nga na magkaroon ng earthquake, pwede maapektuhan yung mga pipe sa ilalim, water mains, gas mains, which is yun nangyari nga dito sa Northridge kung saan sabay na nangyayari yung fire. At nasira din yung mga tubo ng tubig. So, mahalaga sa atin na malaman yung mga possible effects ng earthquakes para sa ating pagde-design ng mga structures or buildings ay makonsider natin itong maaring maging mga problema.
The effects of earthquake on structures. Inertial forces in structures. The generation of inertial forces in a structure is one of the seismic influences that detrimentally affect a structure. When an earthquake causes ground shaking, the base of the building would move, but the roof would be at rest. However, since the walls and columns are attached to it, the roof is dragged with the base of the building. The acceleration or the ground motion generates inertial forces in the structure. These inertial forces are proportional to acceleration of the mass and opposite to the ground motion. For example, you have a table in front of you and an object on top of it, and then you apply a force here on the left side. The tendency of this object is to move towards where the force is applied. Effect of deformations in structures. When a building experiences earthquake and ground shaking occurs, the base of the building moves with the ground shaking. However, the roof movement would be different from that of the base of the structure. This difference in the movement creates internal forces in columns which tend to return the column to its original position. The ground motion produces energy in the structure. This energy is scattered through internal friction within structural members. And as you can see in this figure, you can see this variable u. This variable u represents the movement between the roof and the ground. The larger this variable u, or the horizontal displacement, the larger the energy or the internal forces in columns. Horizontal and vertical shaking. Earthquake causes shaking of the ground in all the three directions, x, y, and z, and the ground shakes randomly back and forth along each of these axis directions. Commonly, structures are designed to withstand vertical loads, so the vertical shaking due to earthquakes is tackled through safety factors used in the design to support vertical loads. The horizontal shaking along X and Y directions remains a concern. In general, those structures that are designed for gravity loads may not be able to safely sustain the effects of the horizontal acceleration. Lateral inertia forces are generated and transferred from polar slabs going to the walls or columns. The structural elements and connections between them must be designed to safely transfer these forces. And walls or columns are the most critical elements in transferring these forces. Walls are relatively thin and often made of brittle material like masonry. Bearing pads uniformly transfer specified vertical loads to the support structure while allowing horizontal movement and rotation. It is commonly used on bridges. It absorbs compressive forces, destructive effects of shock and vibration. It distributes the loads to substructures and allows the main structure to undergo movement or absorb lateral forces without creating any harmful stresses. It also increases the lifespan of the structure because it can accommodate larger movements.
So let us now proceed to the design of buildings for earthquake effects. The behavior of a building during ground vibration is a function of the nature of foundation soil and natural period of vibration of the structure, which depends on the material used in construction, its form, size, and mode of construction, etc. So, ang sabi po dito is yung behavior daw ng isang building during earthquake or ground vibration ay nakadepende sa kung anong type ng soil and kung anong materials yung ginamit sa pagbuo ng isang building. So, kung halimbawa, ang mga materials na ginamit para mabuo yung isang building na iyon is medyo may kamurahan and yung soil na pinagtayuan is hindi ganun kagandahan, ay may tendency talaga na madaling masisira yung building kapag nagkaroon ng earthquake. The structure also gets affected with the duration and intensity of earthquake. IS 1893-2002 specifies seismic coefficients for calculating the design forces for simple structures standing on soil which will not settle or slide much due to loss of strength like liquefaction effect. So, alam naman po natin na due to the intensity and duration of an earthquake, yung ating structure or buildings can still get affected. May chance na magkaroon pa rin ito ng damage. By IS 1893-2002, using seismic coefficient method, we can calculate the design forces na pwede nating gamitin for simple structure na hindi masyadong magkakos ng movement during earthquake because of a loss of strength. In the design of buildings, horizontal forces due to earthquake is considered simultaneously along with the vertical forces. Sabi dito, before tayo mag-design ng isang building, we need to consider the horizontal and vertical forces, so in that case, we can maintain the equilibrium of a building. Makikita rin naman natin sa figure na mayroong horizontal and vertical forces each column. Normally, the natural period of vibration of any structure should not coincide with the predominant period of earthquake excitations. Otherwise, resonance may occur and even the strongest structure may collapse. Thus, while designing the building, following aspects should be looked into. Una is the magnitude and type of earthquake excitation. Aware naman po tayo kung ano-ano ang klase ng magnitude, kaya let's proceed sa type of earthquake excitation. Model analysis of finite element bridge models are performed under earthquake excitations. The goal of model analysis in structural mechanics is to determine the natural mode shapes and frequencies of an object or structure during free vibration. It is common to use the finite element method or FEM to perform this analysis because, like other calculation, using the FEM, the object being analyzed can have arbitrary shape and the results of the calculations are acceptable. Sa madaling salita, ito ang kadalasang ginagamit dahil yung object being analyzed can have any shape and nag-result ito ng natural shape when it's free to move in a certain way. Second is the natural period of vibration of structure, along with its material and mode of construction. Response of structure to earthquake design forces to which the building elements will be subjected and can be calculated by any one of the following methods. So, una is seismic coefficient method. The seismic coefficient method is one of the static procedures for earthquake-resistant design of structures. Horizontal and or vertical forces which are calculated as products of the seismic coefficients KH, KV, and the weight of the structures are applied to the structures as shown. Ito po yung figure na mayroong KH and KV. The stability and the deformation of the structures and the stress and the strain of each structural member are examined against the horizontal and or vertical forces in addition to the vertical load due to the weight of the structure. So by seismic coefficient method using horizontal and vertical forces, we can look kung gaano ka-stable and yung deformation ng isang structure. Also, the stress and strain na kayang i-handle ng isang structural member, pati na rin yung weight ng structure. The second one is the response spectrum method or modal analysis. Response spectrum analysis is a method to estimate the structural response to short, non-deterministic, transient dynamic events. Examples of such events are earthquakes and shocks. Since the exact time history of the load is not known, it is difficult to perform a time-dependent analysis. Due to short length of the event, it cannot be considered as an ergodic stationary process, so a random response approach is not applicable either. Dito sa method na ito ay inaalam natin yung maging reaction ng structure sa isang short-term dynamic events, kagaya na lamang ng earthquake. Pero since hindi natin kayang alamin kung anong oras pwede mangyari ito, mahirap magsagawa ng isang time-based analysis. So, yung random response to the event is not a good idea dahil hindi rin ito magtatagal. The third and last is the time history analysis. Time history analysis is a step-by-step analysis of the dynamic response of a structure to a specified loading that may vary with time. Time history analysis is used to determine the seismic response of a structure under dynamic loading of representative earthquake. In this method, tinitingnan ng time history analysis kung paano mag-respond ang structure to a certain load na nagbabago over time. It looks at how a structure moves when it is under that load. So, nagkaiba ang time history analysis at saka ang response spectrum analysis. A history analysis is based on the strength of earthquakes that happened in the past when they happened in the same place over and over again. Samantalang ang response spectrum analysis naman shows how a structure moves when the ground speeds up the most. It can help you figure out how well a structure can withstand other types of stress. Depending upon the complexity and importance of structure, any one of the above three methods can be adopted. Her only seismic coefficient method is described as this is the most common method. Earthquake forces can be calculated in any direction of structure, but the most damaging direction is horizontal.
So for computation, i-discuss po muna natin yung code NIS 1893 Criteria for Earthquake-Resistant Design of Structures. So ito pong code na to is magagamit natin mamaya sa pagsasolve ng problem mamaya. And ito pong code na to is sinamary ko na din para mas madali po natin maintindihan yung computation sa topic namin. So umpisahan muna natin i-define si design seismic base shear. So, sabi dito, the total design lateral force or design seismic base shear, VB, along any principal direction shall be determined by the following expression. VB is equal to AHW. Si VB, yung total lateral force na nag-a-act sa building. So, kung gusto mo siyang i-distribute per floor, so ito ang gagamitin mong formula. So, bago yan, i-define muna natin si AHW. So, si AH, sabi dito, design horizontal acceleration spectrum value as per 6.4.2 using the fundamental natural period TA as per 7.6 in considered direction of vibration. So, punta muna tayo sa 6.4.2. So, sabi dito, si AH daw is equal kay Zi over 2R SA over G. No? Si I is ito, importance factor. Tapos itong the rest is sa next slide, papaliwanag ko. So, si I muna tayo dito, importance factor. Nakadepende siya dito sa structure, kung anong structure. Kung siya ba is hospitals, schools, monumental structures, emergency buildings, like telephone exchange, television station, and yan, lahat na nakasulat dito. Ang katumbas niya daw is 1.5. So, yung lahat ng hindi nakasulat dito is 1.0. So, sabi din dito sa notes, the design engineer may choose value of importance factor I greater than mentioned above. So, 2 building not covered in SI number I and 2 above may be designed for higher value of I depending on economy, strategy, consideration like multi-story buildings having several residential units. So, yun lang naman yon nasabi dito kay I. So, si SA over G, kapartner niya is ito, si TA. So, may limit kasi to si SA over G. Ito si SA over G is the type, kung anong type ng soil. Kung ba siya medium or hard. Tapos yon is may limit na kakailanganin si TA. No? So, para mas maliwanagan kayo, i-discuss ko din siya sa next slide. So, i-discuss ko muna si TA. Si TA is the approximate fundamental natural period of vibration in seconds of all other buildings, including moment-resisting frame buildings with brick infill panels, may be estimated by the empirical expression. Na TA is equal to 0.09, ay may H to. H over square root ng D. Where H is height of building in meter and D is the base dimension of the building. So, yun lang yon. Tapos, tingin ka lang dun sa table nito mamaya. Sa next slide. Yun, makukuha mo na tong value nitong SA over G. Si I dito. So, si Z at R na lang ang kulang. Si Z naman is, sa next slide din, papakita din yung slide ni Z. Si Z is the zone. Kung anong type ng zone. Kung 1, 2, 3, 4. Tapos may equivalent value din siya. Kung binigay siya, bibigay naman tong mga to sa problem. No? So, yon punta naman tayo kay W. So, si W naman is the seismic weight of the building as per 7.4.2. So, ito, the seismic weight of the whole building is the sum, sum siya ng dead load plus live load. No? Yun lang si W. So, sabi ko nga kanina dito, kung gusto mong i-distribute si VB per floor, ito ang gagamitin mo na formula. Punta tayo kay vertical distribution of base shear to different floor levels. So, yun, nakasulat naman. So, the design base shear VB computed in 7.5.3 shall be distributed along height of the building as per the following expression. QI is equal to VB WI HI squared all over summation ng WH squared, ito is from first floor hanggang kung ilang floor. So, CQI is the design lateral force at floor I. Kung ito ay first floor, edi itong numerator mo is first floor, no? Kung ito is second floor, itong W at H sa numerator is pang second floor, no? So, yun, makukuha mo na. Dapat ang total ni QI, Q from first floor hanggang kung ilang floor is dapat equal siya kay VB. Para ma-check mo kung tama yung iyong nakukuha sagot. So, ano pa ba? So, ito. So, isa pa pala sa pagkuha naman ng live load is may sinusunod din. So, sabi dito sa table, impose uniformly distributed floor load kilonewton per m squared. Ito is isang condition, 1 up to 3 is 25% daw. And yung above 3% na, like 4, 3.1, 3.2, above ay 50% na ang gagamitin natin. No? Kung ang binigay sa problem is 4 kilonewton m squared, edi ang gagamitin natin live load is 2 kilonewton m squared. So, yon. Tapos isa pa, sabi din dito sa 7.3.2, for calculating the design seismic force of the structure, the imposed load on roof need not to be considered. So, yon, si roof sa live load is hindi na natin kino-considered. So, next slide. Next slide is ito, si Zay. Ito yung sinasabi ko kanina, si Zay. So, the values of seismic zone factor Zay reflect more realistic values of effective peak ground acceleration under maximum considered earthquake MCE in each seismic zone. So, ito yon. So, pag binibigay naman to sa problem, seismic zone or seismic intensity. No, maalin dito sa dalawang to. No, ito lang tatandaan natin. Na low is 2, 3 is moderate, 4 is severe, 5 is very severe. No, tapos sila is merong equivalent zone factor na 0.1, 0.16, 0.24 at 0.36. Yan. So, ito yung gagamitin mong values. Depende sa problem. So, next naman yung SA over G. So, ito din yung sinasabi ko kanina. No? Depende siya kung hard soil, medium soil, at soft soil. Sinasabi din to sa problem. Itong mga to. So, dito sa SA over G, sabi ko din, kailangan natin si T. Ito si T. Yung 0.09 H all over square root ng D. No? Kung anong value dyan, kung wari siya ay medium soil, pumatak yung value mo ay 0.12. Edi dito siya sa 2.5. So, kung pumatak siya sa gitna ng 0 at 0.10, edi yung nakuha mong T is isasubstitute mo lang sa equation na to. Tapos yun ang gagamitin mong value. The 1 plus 15 times T is equal to kung anong sagot nun. Kung yun ang gagamitin mong SA over G. No? So yun lang yun. So, next slide. Yan. Ito yung si R. Yung nakalimutan ko kanina sa AH. So, si R, ini-indicate din to sa problem, response reduction factor. Kung ordinary RC moment resisting frame is 3, ang equivalent niya. Pag special RC moment resisting frame naman or SMRF is 5, no? Pag sa steel frame with concentric braces is 4.0. Eccentric braces 5.0. Um, Steel moment resisting frame design as per SP6 is 5.0. Load bearing reinforced is 1.5. Reinforced with horizontal RC 2.5. Reinforced with horizontal RC is 3.0. Ordinary reinforced concrete shear naman is 3. Yun. The rest is ganito. Dito lang tayo magbe-base, no? Sa code na gagamitin. Ito is parang yung AH naman is parang substitution lang, no, sa code. So, yun lang yung code. So, proceed na tayo sa problem solving. Ito. So the plan and elevation of a 3-story RCC school building in shown below. The intensity of dead load is 12 kilonewton m squared, including columns, beams, and walls. And floors are to cater an imposed load of 4 kilonewton m squared. The building is situated in zone 4. Yun, binabanggit. The design of soil encountered in medium soil, and it is proposed to design the building with a special moment resisting frame. Ito yung R. So determine the seismic force and shear at each floor level using static coefficient method. So isolve ko lang siya sa paint. So tuloy lang natin. So, ang hinahanap dito sa problem nito is seismic forces and shear at each floor. So, si QI saka si VB. No? Si VB, may formula yan. AHW. So, si AH, may formula din yan. Itong lahat ng to is nasa problem. No, given to lahat sa problem. So, lista muna natin isa-isa. Zay, sabi dito, zone 4. E di, ang kanyang zone factor, tingin lang tayo dito. 0.24. 0.24. Si I naman, ito. Ito yung kanyang keyword. 3-story RCC school building. Punta tayo sa table 6. Yun, school, 1.5. Hindi siya ay 1.5. No, si R, ito naman ang kanya. Special moment resisting frame. Na ano ba daw yon? Nandito. Yon. 5.0. Hindi 5.0. Si SA over G. Sabi ko nga, para makuha si SA over G, kailangan muna ng T. Si T may formula yan. Ito. 0.9 may H to. Sabi ko din kanina may H. Di 0.09 H lang. H ng square root ng D. So, si H, ito lang yan. No? Di 9. 9 siya. So, si D, ito yon base. No? Sabi dito, D is the base dimension. So, ito is 8. No? So, siya ay 0.286. Hindi. Tingin tayo sa table. Ito. Wait. Tingnan muna natin kung anong type ng soil. Sabi dito, medium soil daw. Hindi, tingin tayo sa medium soil. Ang T natin ay 0.286. So, pumasok siya sa condition na to. Medium. Tapos 0. Between siya ng 0.1 to 0.55. No? Di 2.5 si SA over G. 2.5. Hindi, meron na tayong AH. Substitute na lang lahat. So, ang nakuha kong AH dito ay 0.09. No? Si W naman ay, di ba sabi ko si W dead load plus live load? Yan. So, kailangan natin ng dead load. Si dead load ng floor para kay floor, saka dead load para kay roof. Si dead load, sinabi 12, na 12 kN per ems squared. So, para makuha natin yung total dead load kay floor, kailangan natin ng floor area. No, ito is 5, tapos ito ay 8. No, edi, 10 pala to, tapos sorry, 8. Edi, 10 times 8, 80. 80 lang ang floor area natin. Ang squared. Di bali ito, 80 times 12. 80 times 12 ay 960. No? So, ganun din. Same na, iisa naman ang binigay ng floor area. Isa din dead load. Di 960. Sa floor at roof. So, pagdating sa live load kay floor, si floor ay 80 din. 80 times ito imposed load. Kaso, sabi nga dito, may sinusunod tayong table. Ayan. Ang binigay sa problem is 4 for kn. So, above 3 siya. So, ang 50% ng 4, dito lang yon. No, dito 160. Si live load ng roof, sabi ko nga kanina, hindi na yan kinoconsider. Ito, dito sa 7.3.2. For calculating the design seismic force, the imposed load on roof ay hindi na daw na-consider. So, yun lang yun. So, para makuha si W, si W is, so, dead load plus live load, floor. So, ito is floor. Ito kami consider ng roof. No? Hindi dalawa yun. Hindi dalawa na dead load plus live load. Hindi 960. Ito yun. Tapos live load ng floor, 160. Plus 160. So, plus, ito, iisa na. Isa na yan, no? Di 960 plus 0. No? The W niya is 32. So, meron ka na niyan. So, substitute na lang. Meron ka ng AH, meron ka ng W. So, makukuha mo na si VB. So, isulat ko na lang dito. Si VB natin ay 288. 288 kilonewton. Yan. Yan si VB natin. Pag pinag-times si 32 at si 0.09, AH times W. Ito na yung una. So, ang sabi, shear at each floor naman. Diba, sabi ko kanina, kung para makuha yung each floor, ito ang gagamitin formula. No? So, copy ko lang. So, QI is equal to VB times WI squared. Tapos, 3-story siya. Hindi, first floor to 3. Summation ng W, H squared. So, kunin muna natin to para mas madali. No? So, sa first floor, di ba siya ay, ito ay 120, no? Dead load plus live load. 960 plus 160, 1120. Ito din. 1120. Ito 960. No, total 32. Kaya nga naging 32 yan. No. Di sa first floor, ito. Di 120 times 3 squared. No? W first floor times height ng first floor. Yan. Is equal to 1120 times 3 squared. 180. Yan. So, second floor, palitan lang natin 1120 times 6 squared. No? Ayan siya, oh. 6 squared na. Di equal siya sa 4320. So, si third, 960 times 9 squared. 960 times 9 squared. 7760. 77760. So, kung ito-total natin yan, ito yon, summation ng WH squared from first floor to third floor. D plus 4320 plus 180. 128 ang 160. No? So, substitute lang natin. Si Q1 is 288, si VB. Ito, pang first floor, ito. Ito't maka-equals. Di 180, ito total. 128, 160. So, si QI natin ay 288 times 180 divide 128, 160. 22.65. Ito, decimal ko na lang. Si Q3, si Q2, palitan mo lang to. No? Yun lang naman ang pagbago-bago. Yan. Ang ipapalit mo naman is ito. Wait lang. Second floor. Ito. 4320. 4320. Calculating ko lang. 4320. 90.61 na lang. Si Q2, si Q3 pala. Ito naman ang sa kanya. Copy ko lang. Yan. Tapos ito, palitan natin. Ito, pang third floor. Yan. So, si Q3 ay calculating ko lang. 77760. 174.74. So, check natin kung mag-i-equal siya kay VB. Dapat siya ay 288. Kaso, stored value ang gagamitin ko. Ito, pag-add ko. Yan, 288. 288. Equal siya sa Q1 to 3. Pag pinag-add. So, tama ang mga nakukuha nating value. So, i-box lang natin. Ito. Ito. Saka ito. So, 288, no? Chinecking natin. Pag pinag-add mo to, tatlo na to, ito. So, kung i-drawing natin yan, dito. Kunin ko lang ito. Dito na natin ilagay. So, ito daw, sa third floor, meron dito 174.74. Second floor, 90.61. Tapos, first floor ay 22.65. So, kung i-share ang moment natin yan, pan-checking din yun eh. No, di ba yan ay ganito lang? So, same direction sila. Di padagdag lang yan na padagdag. So, dini ko na lang lalagay direction. Di 174. So, bababa kasi walang loadings. No? Di 17, kung ari 174, itong part na to. bumaba lang, 174 pa rin to. Plus 90.61. Hindi yun ay 174.61. 265. 265.35. Ito is 174.74. So, bumaba lang. Wala naman ding loadings. No? Tapos, plus 22.65 pa. 0.65. Yun, 288. 288. Yan, sakto. No? So, kung i-drawing natin yan, ulit, nakaganto yan. Yan. Karne ko lang. Yan. Ito si Q3, Q2, Q1. Ito na yung sagot natin. Yan. Yung part na yan. Saka ito. Si VB. Yun. Yun lang. Yung topic natin. Kanta lang. Sa code lang siya magbe-base.